can start. Are you good? Okay, so welcome everybody to the last seminar. This seminar is called Search for New Physics in Accelerators and the Cosmos. So today we have the presentation of Dr. Sasso. Dr. Sasso began his studies as an undergraduate at Harvard, took his master's at Cambridge, and earned his PhD from the University of Oxford. He then held postdoctoral fellowship at Leiden University and MIT before assuming his current dual appointments. He is a faculty member at the University of Ljubljana, I think so, and a fellow at the Higgs Center for Theoretical Physics at the University of Edinburgh. So welcome, Dr. Sasso, and please, whenever you're ready, go ahead.
Thank you very much. Give me just 1 second, okay? Just one second.
Okay, sure.
Okay, good. Now I think I can hear you, and it's yeah.
Okay, thank you.
Great. Yeah, thank you very much for the invitation to speak at this online event, and thanks for those who are here. And so there's not many of us, so basically, if you have any questions, you can just, at any point stop me. So, okay, so what do I want to talk about today? So I want to talk about the theory of black holes and holography, and I want to tell you about some new results of how various properties that we've been learning about that come from the theory of black hole perturbations, how this sort of interplays with holographic duality, so ADS-CFT correspondence, and what this has to do on the other side of things with quantum field theory. So as I don't really know the group, do stop me, okay, if something is unfamiliar. So just to sort of motivate things briefly, I am mostly interested in learning about thermal field theory. So for example, I'm interested in the kind of states of matter that are made of particles or whatever. They're described, let's say, by some kind of quantum field theory. But what is very interesting in particular is when these states are strongly interacting and they behave collectively as sort of plasmas or fluids. So there are some, on top you see an example of various things. There's the sun, that's a plasma. This is a neutron star, which can also be understood as a plasma. Here is a picture of a cartoon of sort of a quark gluon plasma, which is also a plasma. So a lot of things we'll be talking about today, so really will be sort of results about quantum field theory, thermal field theory. So here's a partition function of something that I'll be thinking about. So I have some partition function that's put into a thermal density matrix, e to the minus beta h, where beta is 1 over the temperature, and there's some action. Okay, we'll say more about these things later. Now, what is sort of really nice about this recent progress in the field of ADS-CFT or holography is that a lot of these questions in toy models of plasmas can be translated into problems of black holes, and in a very concrete sense, you can also think of a black hole as a thermal state. So here's also a picture of a black hole. So I will be talking about spectra. So what I mean by spectra is the following. So let's say you take, some kind of a thermal system, some quantum field theory in my thermal density matrix, and you perturb this system. So you kick the system with some source J, and you measure in linear response theory the expectation value of some quantum operator O in the thermal state in the presence of this source J. Okay. Now, as you I'm sure know, the response to linear order is encoded entirely in retarded two-point functions GR. Okay, so here's my definition of the retarded two-point function of these two quantum operators, O at time x at some time and x, and O at 0, 0. And what is very important is that in a thermal state, this will tell me about the relaxation of the system back to equilibrium. Okay, so we will actually, most of the time, we'll be looking at these correlation functions, retarded correlation functions in momentum space. So I will be Fourier transforming everything to frequency and momentum space. I will be calling Q my momentum, okay? And omega is the frequency. So I will be looking at the analytic structure of such things, complex analytic structure of such things. So, okay, so typically, you have some function, your retarded correlation function of some operator. Typically, we'll be looking at energy and momentum. It has some numerator and it has some denominator. Now, what is very important is that the denominator of this thing, so this is, here, the denominator in the frequency space tells you about the physical excitations of your system, okay? So here, if you go up to this line, here you can think of this, you have some, so your spectrum is sort of Fourier decomposed, and there's some infinite number of these frequencies. They're called quasi-normal frequencies because sort of they're not real. They have imaginary parts, so they're relaxing. And this is sort of telling you about the approach down to equilibrium. And wherever you have a frequency, okay, which is sort of telling you about how your system is relaxing to equilibrium, in momentum space, what you find is that for every frequency where there's a, an excitation that takes you to equilibrium, I will be plotting these types of diagrams, which you see here on the bottom. Hopefully you can see my cursor. So what am I plotting here? So this is the analytic structure of the correlation function. I'm fixing my temperature, I'm fixing all the parameters of the QFT. Also, I'm fixing my Q, so my momentum, the wave vector of the mode is fixed. And I'm showing you locations in the complex omega plane where the correlation function G has a pole. So where it's, 1 over 0. So you can think of this as, in the denominator, some infinite product. There's an infinite number of such poles. And at every omega, where there's a physical excitation, at some Q, I will draw a dot. Okay, so the dots represent my physical excitations, and this is what I call the spectrum. This is the spectrum of the correlation function. Now, what is really nice is that via this holographic duality, right? So I will not go into any details about holographic duality, but you should just think of it as a sort of a black box thing that for certain types of thermal quantum field theory, instead of doing really difficult calculations in, let's say, 4-dimensional QFT, you can actually compute the spectrum of the QFT by instead looking at a higher dimensional classical theory of gravity in space with a negative cosmological constant, so lambda is negative. These are, so-called asymptotically anti-de Sitter spaces, and there's some kind of a black hole living in this 5-dimensional space in the middle, and you can, this is kind of a finite space, and at the boundary of the space, the boundary is obviously 4-dimensional. Your quantum field theory is living on the boundary. Okay, so this is called holography, ADS-CFT correspondence. And there's a holographic dictionary between observables on one side of the duality and the other side of the duality. And in particular, to get to the spectrum of your thermal correlation function, what you need to do is go to this 5-dimensional black hole and compute its perturbations. So the spectrum of perturbations, also known as quasi-normal modes. Okay? So these are, on one side, the quasi-normal modes of a 5-dimensional black hole. On the other side, they are the poles of the correlation function in some thermal strongly coupled quantum field theory. Now, again, to be more precise, these types of quantum field theories that I'll be looking here are typically supersymmetric theories that arise from string theory, like n equals to 4 super Young Mills. We do not know what the holographic dual to QCD is, let's say, but one hopes that if you are able to study at least some strongly coupled field theories, you can learn some generic properties about how such theories should behave. Okay, good. So, all right, so let's go to sort of this discussion of these spectra, right? So if I sort of simplify my life a little bit, so what is if you go to like a quantum field theory book like Peskin and Schroeder, people talk about spectra there too. Now, of course, those spectra are typically much simpler because people look at this at 0 temperature. Now, let's say you take some, scalar field phi and you compute a 2-point function of the scalar field, and you can equally ask what is the analytic structure of such a correlator. So here, of course, because this is a 0 temperature theory, so Lorentz invariance is not broken, you can draw it in the complex p² plane. And what you find is, some poles and some cuts. So wherever you have a pole, this is my dot, you will have either the isolated pole corresponding to the massive excitation. This is the the massive boson excitations. You can also have some poles that come from bound states that are here. And then after this threshold of 2m squared, you will get a continuum of states. And this is in the analytic structure. What this will show up is as a branch cut. Okay, this is what, a typical quantum field theory at 0 temperature for the correlation function of fundamental field would look like. Now, I will not be interested in fundamental fields. I will be interested in correlation functions of the energy momentum tensor. So energy and momentum. Okay, now the question is, what do we know about such things in generic QFTs? And the answer is not a whole lot. So at finite temperature, these are composite operators. It's actually very difficult to compute the spectrum. So what we do know is that when the theory has zero coupling, so it's a free theory, the spectrum looks kind of like this. So you will typically find an infinite sequence of branch cuts that kind of come at these minus 4 pi ti, minus 8 pi ti, 12 pi ti, and so on. Now, on the other hand, what I already told you is that the typical correlation functions from holography, which is actually computing your quantum field theory at very, very strong coupling, does not have any cuts. It will typically have only poles. Okay, so one of the questions is, how do you go from one to another? And one of the reasons why holography is so good is because you can actually compute this. In perturbation theory, it's extremely difficult at any finite coupling to get the actual structure of the correlator. In almost no theories do we know what the spectrum should look like. Whereas in holography, this is much simpler because actually this duality reduces the problem not down to computing an infinite number of Feynman diagrams, but to solving some simple differential equations. So this is why this can be done. Okay, good. Now, okay. A large part of what I will also be talking about is, different parts of the spectrum. So you see, so the spectrum sort of looks like this. We call this kind of a Christmas tree. So near the origin of the complex omega plane, you have a sort of a special pole, typically. This one is sort of drawn with a bigger dot. And this pole knows about what we call hydrodynamics, okay? So these are thermal field theories. So the low energy part of a thermal field theory is typically described by a theory of hydrodynamics. So the theory of fluids. So the question is, what is hydrodynamics? So very briefly, hydrodynamics is a theory of conserved global operators, as I already said, and it expresses the conservation laws. So for example, the conservation of T mu nu is a hydrodynamic equation of motion. Okay, this is what in the end gives you your Euler equation, your Navier-Stokes equation. So in principle, classical hydrodynamics, you should really think of as an infinite order gradient expansion. So for the more QFT people, this is kind of like it's a derivative expansion theory, like some kind of chiral Lagrangian or something like this. So you can take your energy momentum tensor, and in principle, you could expand it to an infinite order in derivatives around your velocity of the fluid and your temperature field of the fluid. So the details are not so important. What is important is that the solutions, so the conservation equations, so this, grad mu T mu nu is equal to 0, for the hydrodynamic modes, so these are the modes that are closest to the origin of the complex plane, so small omega, which means small energy, can be expressed as infinite order power series. So omega is a function of q for a hydrodynamic mode, will always have the following form. You can write it as an infinite order series that looks like this, with some coefficients alpha n, and these coefficients, of course, depend on the equation of state. They depend on various coefficients like viscosities and so on. Okay, so just to give you a sort of a simple example of this, typical hydrodynamic modes are either diffusive. So if I truncate my series at order q squared, and it's purely imaginary, so it looks like omega is equal to minus I times d, which is called the diffusion constant, times q squared. This is then a purely exponentially damped mode, which just relaxes to equilibrium. Okay, this is diffusion. If you have a real part and an imaginary part like this is called a sound mode. So the real part goes as q, and the imaginary part, the attenuation of the mode, again goes as q squared. Okay, but you should note that in principle, one is really not allowed to truncate the theory at order q squared, unless you have a good reason to do so. In theory, all of these are infinite order series. Okay. Now, so you can ask already the question of what is the analytic structure of hydrodynamics? Well, of classical hydrodynamics is just a single pole. It's just this pole here that I've been showing you, okay? With some, higher power in Q corrections. Now, sort of as a little aside, we now actually know how to write down really an effective field theory of hydro, and we know how to compute loop corrections to the hydrodynamic theory. And one interesting thing is that, for example, with loop corrections, you will just generically get cuts again. So poles develop also cuts. There's a sort of a funny prediction that we can make from our effective field theory of hydro is that you will get an analytic structure where the diffusive pole splits into two, and you will get an infinite sequence of branch points at omega is equal to minus idq squared over m plus 1, where n is the number of loops that you include into this effective field theory. The details are not important, but just for you to know that, again, as soon as you start including loops, you will get cuts. Something quite similar also transpires from kinetic theory. So if you do Boltzmann equation or things like this, sort of standard kinetic theory, again, you find a sort of an interplay of poles and cuts. And you should think of this as computing your physics around weak coupling. Okay, so this is like perturbation theory in QFT, which is kind of similar to kinetic theory. Now, on the other hand, if you really go from strong coupling towards weak coupling with the help of holography, then what you generically find, and we've shown this over numerous papers, is that you just have presence of poles. And what is a very sort of interesting thing is that we actually understand how poles become cuts as you go from strong coupling towards weakly coupled physics. So what generically happens is as follows. So you can see there's a picture here. So as you make coupling smaller and smaller, these poles come closer and closer and closer together. And in the limit, they will kind of stretch out to the real axis. And what you always have, we can prove this, is a sequence, infinite sequence of pole 0, pole 0, pole 0, pole 0 in the correlation function. In the limit, the residues of the poles go to 0. So, and then in complex analysis, this is the sort of a standard representation of a branch cut. We understand this very well, okay? Another thing, for example, this is something that will give you only the leading cut. We understand also in sort of this higher perturbation theory coming from string theory and supergravity, how in principle you can also generate other cuts, these sort of subsequent branches that may potentially lead to this infinite sequence of cuts. Okay, so one thing that's very interesting is from the strong coupling to the weakly coupled regime, we understand this quite well, I would say, because of holography. Going from weak coupling to strong coupling using QFT methods is much harder, and there the picture is sort of murky. Okay, so we don't really know what will happen there. What I mean by this is generically prediction is that you have poles and cuts, but it is not clear that maybe after some resummation, I don't know, Dyson type resummation, these kinds of things like Bethe-Salpeter in thermal field theory, maybe the cuts will dissolve into poles. This is not known. Okay, this is just to sort of to tell you what is the cutting edge of what we know about spectra of thermal correlation functions. So for everything else that I'm going to talk about today, I will assume that there are only poles. So poles in complex analysis. So this means that these correlation functions G, the 2-point correlation functions of energy momentum tensor or currents or composite operators like this, are meromorphic functions. Meromorphic meaning, in complex analysis that they're only simple poles, no cuts, so no Riemann surfaces. Okay. Now, so this is the setup. Now, maybe this is a good time to pause. So, if you have any questions, maybe this is a good time to stop. So, I'll be looking at structures of correlation functions in QFT with the help of holography, so black holes, and everything that I will be saying will have this kind of a structure. Sorry, the app is asking me something about it doesn't matter. Okay, anyway, so okay, you can stop me also anytime later. All right. Sorry, I'm not so familiar with the Cisco.
Can you hear
sorry,
me?
do I hear? I can hear you actually, yeah.
What does it mean to be meromorphic? I don't remember that concept.
Yeah, so as I just said, so meromorphic means that it's a complex function which is analytic everywhere except at points. And these points are poles. So they're 1/0 type singularities, okay? They're simple poles in complex analysis. That's what the word meromorphic means. Yeah, this is a meromorphic function. So it's analytic everywhere except at the number of isolated singularities, which are simple poles, like 1/x, 1/x squared, or something like this. Okay, but there's no logarithm of x. There's no square root of x. There's nothing that would give you a rise to a branch cut. Okay.
Okay, thanks.
Yeah. Good. This is important, at least to get the words right, because everything from now on will be about meromorphic functions. Okay, so now there's sort of three main results that I want to tell you about, which come from the analysis of such spectra. So I'll tell you how actually this entire spectrum. I will go through this quickly because this is sort of a slightly involved complex analysis, but just so you get the point. So I will tell you about how actually the entire spectrum, all of these physical excitations, can be reconstructed from a single one. Then I will tell you how even the single one can be reconstructed essentially just by knowing some special property of black hole fluctuations. And then in the end, I will tell you about this sort of latest thing that we discovered, which is called the spectral duality relation, which is a result, again, about black hole perturbations. So, okay, so I'll be citing a bunch of papers. This is coming from a paper with my PhD student who graduated recently. So what is the main statement? I will not prove this, but it's actually not too hard to sort of understand why this must be true. So, okay, so over the years, I told you about this, hydrodynamic series. So the hydrodynamic dispersion relation is an infinite series in powers of Q. So the first important statement is to actually remember that. So we were able to prove that these series have a finite radius of convergence. Okay, this is very important. The series are convergent in some finite region of momentum Q. Now, if you look at, in terms of complex analysis, just a little bit of that, what that means is that the function omega is a function of Q. So this is now analytic structure of this function omega of Q for the hydrodynamic series. This function is holomorphic, analytic in a disk, all right? That's this green region. And then, this analyticity dies somewhere. It has some branch points somewhere outside of this. And, there are good reasons why this happens, but sort of the function does have a holomorphic disk. So it's analytic and it converges. Now, what does this mean? So this means that actually you can use complex analysis of such functions to understand not only this leading hydrodynamic mode, but essentially you can figure out the dispersion relations of all of the other modes. So how does this work? So you start from the hydro mode, and then somewhere in your complexified momentum and frequency space, what happens is that the hydro mode will move around the complex plane, and the other point will also move around it, and at some point they will collide. So whenever two modes collide, this is where you get a branch point in the complex Q plane. This is the, you get a branch point, and at the branch point, it's essentially a Riemann surface with two sheets. So then you can use some, sort of complex analysis, and you can do the following thing. So you can start from this hydro series. So the series here is just determined by hydrodynamics. It's an infinite series. And now you can use a bunch of theorems. And there's something called the Darboux theorem of complex analysis. And you can find where in the space the mode will collide into something else, into some other physical mode. Then you can actually re-expand that mode around the branch point. And now you know that actually this branch point will be of order 2. You can also figure this out from the Darboux theorem. So what this actually means is that you now have an expansion of your hydrodynamic mode, omega 0, as here, expanded around some other point in the complex plane. And because you know that this is a branch point of order 2, there's also a second solution. This is like, every time you solve a quadratic equation, you get two solutions with plus and minus. It's something like this, okay? It's just this is generalized to a large series, and this is called the Puiseux theorem. So the physical significance of this is that the second solution, the one with all sorts of minuses in the expansion, is actually the second mode at the position where it collided with the hydro mode. And then what you can just do is just, so you start from the hydro mode, you re-expand around this branch point, you go to the second branch of the Riemann surface, and you know this your second mode. And then again, you look at where this collides with something else, and you re-expand and you re-expand. And what is very nice is that in this way, at least theoretically, one can go from the infrared of the theory and just use complex analysis to reconstruct the spectrum of all the other higher energy modes. Okay, so we actually do this in our paper explicitly. So this is done for four-dimensional anti-de Sitter Schwarzschild black brane. If you want, this is by ADS-CFT. This is dual to something called an M2 theory, ABJM theory. The details are not important, but we have actually a numerical procedure for how to do this. So for example, if we compute the first 300 coefficients of the hydro mode, then we can go through this procedure and compute the second mode, okay? And we can compute all sorts of properties and we check numerically that this is actually correct. And then we can go, use this first gapped mode and, analytically continue, then expand around another branch point and so on. So basically you can kind of walk around this complex plane and you can figure out from one mode, at least in principle. It's not particularly practical. It's very complicated. And, at least sort of somehow the order of the number of coefficients you get faithfully at every next order is very small. But if you knew all of the coefficients, then you could do everything. We can show this, at least sort of prove it. Yeah, so what is maybe most interesting about this is that sort of ideologically this works, okay? So from the infrared, you can go all the way to the ultraviolet. Now, this was just as a brief statement. Now I want to go to something sort of more recent, and I want to talk about first something that we sort of discovered in 2017 in relation to the theory of quantum chaos, and it's called pole skipping. So what is pole skipping? So in this whole world of looking at correlation functions, we found that there's some special points of the correlation function GR where you don't only have a pole, but it so happens that the residue of the pole can also be zero. So it can sometimes happen that the location of the pole of the function crosses the zero of the function, okay? So formally speaking, your correlation function is 0 over 0. What this gives you is some, the function there is regular, but it's multi-valued. So its value depends on how you approach these special points. These are, kind of special points of 0 over 0, which have kind of, they behave very strangely in complex analysis, but it turns out, and this is what we were able to show, that the gravitational perturbations around black holes have, an infinite number of such points. So in this complex omega complex Q space, there's an infinite number of such pole skipping points where something bizarre happens and, the correlation function in the dual QFT will be 0 over 0. As I said, we originally found this from connection to quantum chaos. This is not too important for the talk today. What is important is that an infinite number of such points exists, and the locations always happen at integer multiples of negative Matsubara frequencies. So, Matsubara frequencies are 2 pi t. So these points will always happen at omega that is equal to minus 2 pi t I times n, where m is a non-negative integer. The only one such point exists for n is equal to -1, and that's the one related to quantum chaos, which I will not discuss today. Okay, good. So what does this mean? So now this means in practice the following. So let's say I take my diffusive mode. So my diffusive mode is now, my hydrodynamic mode expanded to an infinite order. My first order term is minus IDQ squared, and then there's an infinite series of higher and higher order terms. Now, in these kinds of theories, what I can do is the following. So let's say I take my Q and I make it bigger and bigger and bigger. So what this diffusive pole will do is, it starts at 0 at the origin, and it will stay purely imaginary. So it will just go down the imaginary axis as I make Q larger. As it does this, it goes through, of course, all the Matsubaras. At some point it goes through all of the minus 2 pi t I times n. And actually, in one of my papers in 2021, what was actually quite interesting was that in 4 dimensions, 4-dimensional gravity, which is dual to 3-dimensional quantum field theory, I was able to find this analytically. I didn't know why, but it just so happened that I could find these locations analytically. I will tell you there's a special reason why this can be done in 4D and not in higher dimensions, even though it still exists in higher dimensions. Anyway, so this is just some more numerics showing that this dispersion relation of the diffusive mode indeed goes through all of these pole skipping points, okay? All right, now the claim is that actually, if you know only these discrete number of pole skipping points, that's actually enough to completely reconstruct the hydrodynamic mode. Now, one reason why this is nice and practical is because these locations, as it turns out, so these special locations of 0 over 0 are actually very, very easy to compute from gravity, okay? And often you can compute them just analytically. Whereas, for example, the dispersion relations are much, much more complicated to compute. So this is very practical, okay? And also somehow philosophically quite interesting. Now, how are you supposed to do this? It's not very easy because, as you can imagine, so what this is essentially an interpolation problem. So you have a function which has an infinite order of terms that is going through an infinite number of points. And of course, there's typically no unique solution for such things unless the function has some special properties, right? Because you can easily imagine any number of functions going through a discrete number of points, okay? Now, the trick that we kind of figured out how this can be done is as follows. So you can imagine that you're working in d number of dimensions, space-time dimensions, and you can take d to be large. Now, in the large d limit, where you have, a large number of space-time dimensions, you can formally solve all sorts of things because the potential, for example, gravitational potential or Coulomb potential, becomes highly localized, okay? And then what you can develop is a perturbation series in 1 over d, okay? And then let's say you're able to solve this, then you can set d to 4 and you will get a result. By the way, one can do this in quantum mechanics, for example, to compute the energy spectrum of helium or things like this. It's actually quite a powerful method, all right? So we do something similar here. And the reason why this works here is that, so we show that this hydro series, which is an infinite series in powers of q, if you also do a double series, so not only power series in q, but also you expand in 1 over d, 1 over the number of dimensions, what happens is that the series truncates. Okay, so think of capital Q as just q. Okay, q times square root d. This is some scaling, which is not so important. So what happens is that in the infinite dimension limit, this hydro series truncates at first order. It's only the purely diffusive term that contributes. If you go to 1 over d squared, there's one extra term. If you go to 1 over d cubed, the series truncates at q to the 6. If you go to 1 over d to the 4, the series truncates at 1 over q to the 8. Okay? So now, at any order in 1 over d, the function still passes through all of the pole skipping points. Now, this means that at every order of 1 over d, what you're really doing now is fitting a finite order polynomial to an infinite number of points, which you can do uniquely. Okay, so using this trick, we show that you can actually uniquely solve the problem. Then there's all sorts of sort of complications and how you're actually supposed to do this, doing some analytic continuations. Doing this in practice is quite difficult, but one can do it. And then again, we can actually sort of check numerically that this actually works. So now, okay, so this, I'm trying to kind of reduce the amount of information in the spectrum down to its sort of bare minimum. So now what I told you is the following. So if I know the pole skipping points, which are just these discrete number of points where the correlator is 0 over 0, on the gravity side, it has some special features of what Einstein equations do around the horizon. If anyone's interested, I can tell you later. But this can be done. So from these points, I can reconstruct the hydro mode. And then from the first part of the talk, from the hydro mode, I can, in principle, reconstruct all of the rest of the spectrum. Okay? And actually, you can do this. What is very interesting is that this actually reduces, conceptually, the computation of the entire correlation function down to not even solving a differential equation. It's really just an algebraic manipulation of your black hole near the horizon. Okay, it's somehow conceptually, it's a local expansion around the event horizon, plus computing some complicated determinants and things like this, but all of the information is really encoded there. And then I should also mention there's a very nice result recently from the CERN group around Sasha Zhibuyedov, which is called the thermal product formula. And I will use this later, but what this thermal product formula tells you is that if you know the poles, then you can also get the zeros of the correlation function. So you can actually get everything, okay? From this very, very limited amount of information. Now, for the last part, I want to tell you about some sort of another kind of striking result of how incredibly constrained these generic spectra are, which again, we learned from the physics of black holes. And this is done with my PhD student in Edinburgh, who's finishing this year, Mila Vrbica. And it's a sort of a series of 3 papers where we developed what we now call the spectral duality relation. So what is this, okay? Now, let's go to 4-dimensional gravity. So 4-dimensional gravity, you take a black hole, by holographic dictionary, if it exists, this 4-dimensional gravity theory is dual to some 3-dimensional quantum field theory, typically a conformal field theory, okay, in 3 dimensions. Now, 4-dimensional gravity, or 3D QFT, is special. One reason why it's special is that it has only 2 polarizations, okay? So in 4D gravity, if you fix a direction of momentum q, there are only even modes and odd modes, which you can sort of organize according to how these modes transform with the remaining Z2 transformation. It doesn't matter so much. What I'm really talking about are longitudinal and transverse fluctuations. Okay. Now, as usual, for example, in hydrodynamics, the longitudinal fluctuations will know about sound, and the shear transverse fluctuations will know about diffusion. So in GR language, these are typically called even and odd modes. But okay, so now if I go to flat space, so if I'm working in spaces with 0 cosmological constant, there's actually a very beautiful theorem by Chandrasekhar from the 70s, which says the following thing. So you have these even and odd fluctuations of a black hole in flat space, like, the Schwarzschild black hole in flat space. If you look at the equation that is supposed to give you the quasi-normal modes in even and odd part of the spectrum, the differential equation looks completely different. The odd one looks kind of simple, the even one looks horrendously complicated. And yet, there's something called the isospectrality theorem, which tells you that the spectra of modes is actually equal to each other. So the even and the odd part of the spectrum looks identical, even though the equations, which you need to solve in order to get them, look completely different. Okay, it's a very surprising statement. So what spectral duality relation is an equivalent theorem statement for black holes with a negative cosmological constant in asymptotically anti-de Sitter space, which gives us then by ADS-CFT also results for these dual 3-dimensional quantum field theories. And there's nothing as simple as isospectrality, but there is a precise analytic relation which actually gives you quasi-normal modes in one channel from the quasi-normal modes in the other channel. They're still completely constrained, even though somehow the physics behind it is much more difficult. So the way we were able to derive this is as follows. So I said that there's something special going on in 4D, 3D dualities, and there are many names by which all of this specialness goes by. So if you go to a 3-dimensional quantum field theory, a CFT, what is special about 3-dimensional theories is particle-vortex duality. So either you have particle-vortex duality or S-duality, that's another main name. That's a sort of a special feature of 3-dimensional conformal field theories, okay? You can think of the XY model or something like this. Now in gravity, which is then 4-dimensional by ADS-CFT, what you have is essentially electric-magnetic duality. You have electromagnetic duality for electromagnetic fields. You also have electric magnetic duality for gravity. which goes by the name of Chandrasekhar duality. And it's actually this Chandrasekhar duality, which is, a form of electric-magnetic duality, which exchanges electric to magnetic fields and exchanges even to odd modes that one can use to prove this isospectrality. So it's sort of highly non-trivial. So what we were able to show is that now, actually in general, in these anti-de Sitter spaces, you always have a duality type relation between the correlation functions that are even and correlation functions that are for the odd modes. And it looks like this. So there's G plus for even times G minus for the odd modes is equal universally to omega squared divided by some function. So this function omega star squared of Q is some function which you must determine, but it's actually very easy, again, to determine this. So historically in the GR literature, these were called algebraically special frequencies. And actually, we were able to show that these things are a subset of the pole skipping points. Okay, so pole skipping is a bigger concept. And these algebraically special frequencies, which fix the correlators, the duality between the correlators, are a subset of pole skipping. Okay, so the correlators are fixed in this way. Now, of course, this is not enough. So then on top of this, we use this thermal product formula by the CERN group and all sorts of properties of correlation functions that come from complex analysis. So again, it's very important that these things are meromorphic functions. It's very important to know how they grow at infinity. For example, this is something that you can figure out from operator product expansions and various things like this. And then using this thermal product formula, which essentially says, maybe for experts, it says that the two-sided Whiteman function, this G12, which can be related to the retarded correlator in this particular way, this thermal product formula or hypothesis, it's proven for some classes of theories, not for everything. It says that this has no zeros. Okay, it's highly non-trivial. So it only has poles, and there are no zeros in the complex omega plane. Anyway, these new statements are actually sufficient to now make the following claim. So this is now the spectral duality relation, and it says the following. So if I define the following infinite product, which is some function s of omega and q, and this is 1 plus omega divided by omega star. This is the algebraically special frequency. This is some function, which is easy to compute for any black hole, times the infinite product over all the quasi-normal modes in the even channel and in the odd channel, defined in this way. Then this has the odd part of this is completely universal. So I'm sorry here, I'm K is equal to Q. I was copying something. K momentum is equal to Q here, but okay. So S of omega K minus S of minus omega K, so the odd part of S is completely fixed. So it's 2 times I times some function of K, which again can be computed from the quasi-normal modes, times hyperbolic sine of beta omega over 2. So you can see, so what goes into the left-hand side is just some extremely potentially complicated function of omega. This could be anything. However, all of these theorems say that actually no, it's always sinh of beta omega over 2. That's somehow the the core of the spectral duality. And this actually is extremely constraining. So this equation alone gives you an infinite number of constraints on where these poles can be. So as soon as you move one of the poles in, let's say, the even channel, it constrains completely the odd channel. Okay, everything is very, very tightly constrained, and there are many ways of expressing these. Maybe they're not so interesting. Maybe what is more interesting, I can show you some examples. So, for example, what can you do with this? So you can prove various things. For example, for the current correlators, you can prove sort of a statement people had observed before, that when momentum Q goes to 0, the poles must converge to the Matsubara frequencies. You can also, for example, for the energy momentum sector, you can completely fix the ratio of the diffusion constant of the dual hydro theory to the attenuation gamma of the sound mode. If you remember, gamma acted like kind of like a diffusion constant for the sound mode. It was somewhere long ago on one of the slides, and this is always equal to 2. So this is completely fixed by this duality. And you can see, for example, that more and more modes you include, you get something that looks closer and closer to sine or sinh. This is done for complex values, so sinh, so it looks like a wave. And you see, these are what these algebraically special frequencies are. So for example, for the ADS Schwarzschild black brane, omega star is very, very simple. It's exactly omega star, just goes as q to the 4, which incidentally is precisely this result that I was able to find analytically for pole skipping that I mentioned earlier. And one of the reasons why I can only find it in 4D is because in 5D, 6D, and higher on, there's no duality structure that would make things very, very simple. Okay, so 4D really is special because of this, all of these dualities that exist in this number of dimensions. For Horizon and Nordstrom, you can do similar things and so on. Okay, now you can also take this further and you can expand this to, for example, any pairs of correlators in any number of dimensions. Actually, for example, for scalar operators, this kind of duality relation works for any number in any number of dimensions. In particular, the reason is so this duality reduces to a special limit. So what happens is that this omega star goes to infinity. When it goes to infinity, this first term is just 0. So you have something that looks like a self-duality. G plus G minus is equal to -1. Okay? Now, in such cases, the spectral duality just, there's no more omega star, so it just reduces to a simple form. It's just a product over omega pluses, omega minuses, and it's still constrained by the same thing. And for example, what one can show is that in this case, and also the other case, if you know one spectrum, owing to all of these constraints, so if you know all the omega pluses, you can get all the omega minuses and vice versa. You can also say something quite funny and trivial. So obviously, G of omega times G inverse of omega is equal to 1. Okay, that's a trivial statement. X times 1 over X is equal to 1. Now, this trivially satisfies the spectral duality relation. So what this means is the following. Okay, the poles of G are the poles of G. What are the poles of G inverse? Well, they're the zeros. So this means that actually by the spectral duality for any correlation function itself, if you know the poles, you can compute the zeros of it, just because they act like duals in this type of duality. Okay, so that's kind of a cute little application of this, which also sort of goes back to something I mentioned before, that also knowing this thermal product formula of the CERN group, you can use that also to compute all the zeros. Okay, so finally, as the final application, this spectral duality relation also works just purely from the point of view of quantum field theory for quantum field theories that have a large number of local degrees of freedom. So for any large N field theory, you can do the following thing. So imagine that you start from an ultraviolet fixed point and you want to turn on a double trace deformation that will run down to the infrared fixed point. Okay, what we're also able to show is that the spectrum at the ultraviolet fixed point and the IR fixed point also obeys this spectral duality relation, because for any such flow, G minus G plus you can think of as the UV IR CFTs. Okay, and not only that, we can actually show that anywhere along the RG flow, if you just pick 2 locations along the RG flow, you can do the same thing. So basically, from spectrum anywhere along the RG flow, you can compute the spectrum anywhere else along the RG flow, and then again by this special case of duality, then you can also compute all the zeros, so you get the whole correlation function. A more general statement that I can make is that you can use the same duality relation for any pair of theories that are related by a Legendre transform. And it just so happens that double trace RG deformations really perform a Legendre transform on your field theory. And similarly, an electric magnetic type duality on the boundary, which sort of translates into a particle vortex duality or S duality, can also be thought of in a similar way by a Legendre transform. Okay, good. Here there's some examples of how this actually works in some simple cases of of QFT's dual to gravity. We can check this. For example, maybe for experts, this is a calculation of the BTZ spectrum, which is a three-dimensional black hole dual to some two-dimensional CFT. And we can show that this duality is explicitly verified by having an analytic solution. This is a check. And then, for example, if you go to higher dimensions for these scalar operators, this is an explicit calculation in n equals to 4 super Young-Mills, again, done from the gravity side. And again, we actually also developed now a numerical algorithm that allows us to do all sorts of things. So for example, as I showed you, what you can do concretely, just using this one relation, let's say you know the spectrum at your ultraviolet fixed point. So this is n equals to 4 super Young-Mills for some, scalar primary of certain dimension. Then using this, you can compute the zeros of the correlator. Then using the duality, you can compute the infrared spectrum. And from that, you can compute the infrared part, the infrared zeros. Now, one interesting thing about this that I should sort of, as a little caveat, clarify, what is actually interesting is that it kind of, in this case, it does work kind of like RG in the following sense. So if you know the ultraviolet spectrum, you can completely and uniquely compute everything about IR. So on the other hand, if you know everything about IR, you need to specify one more function of momentum to compute everything about UV. So it's actually, there isn't really any like RG flow or anything like this, but it is sort of interesting that conceptually you do need, a little bit more information here to go from IR up to the UV. Okay, it's just the last thing that I wanted to mention. So, okay, so what is the summary of all this? So hopefully I showed you that, we have lots and lots of techniques now, coming from a combination, sort of merger of gravity, QFT, and complex analysis, that we can use to study these kinds of very interesting structures that are, generically appearing in QFT. What is very interesting is that now knowing all these structures, all sorts of quantum field theories in the large N limit, which are dual to, gravity, are exhibiting very, very, very stringent constraints. Okay, so this, these spectra are extremely rigidly constrained. This is something that I think is new, that people didn't know before, and now we've really quantified lots and lots of these constraints. So basically, lots and lots of things are predetermined. You just need to know one small detail about the spectrum, and then from that you can get all sorts of things. Now, I don't want to sort of overstretch this, because still, you always still need to know, in some sense, an infinite amount of data, but it's sort of infinite, different infinities of how they're reshuffled from either the number of coefficients into, another infinite set of modes and so on. Hopefully, maybe this was clear what I was trying to say. Okay, so these results that I showed you apply directly to gravity and ADS, and because of holography, also on the other side to quantum field theories. This is again thanks to holography that we can say stuff about both sides. Now, the main sort of open question here is, what, if anything, of these things, these methods that we've learned, can we use to say stuff about realistic quantum field theories? This is unclear. Presumably, yes, at least this spectral duality stuff should survive in something with S duality. Hopefully something like this persists if you go away from the large N limit. Certainly, these things exist in gravity, so there it's fine. How exactly this may apply to realistic QFTs is unknown, and I think this is sort of a big open question. Okay. Also for the future, the main obstacle here being it's very, very difficult to do anything exact in QFT at away from the large N limit. Okay, good. So this is kind of everything I wanted to talk about. Thank you for your attention.
Thank you, Dr. Sasso. So let's go for some questions. Let's see if there are any questions. Please just turn on your audio and ask.
Yeah, it's a little bit difficult because I don't know the group, so I don't know if who knows what. It's a little tricky. Yeah. It's easier if you visit the place actually, and then you meet people over lunch and you hear what people actually work on.
Hi, can you hear me? Hello.
Yes. Yeah.
Yes, Jonathan.
Thank you for your nice talk. You mentioned something about super young means n equal 4, but but what about, I mean, supergravity in n equal 8? It is, could be work or
Well, in how many dimensions? In 4 dimensions, I guess.
yes, d equal 4.
Yeah, right.
Or only works
Well,
for super young means theories.
you see, so what we're normally doing here is making statements about QFTs without gravity.
Without
Because, holography relates QFT to gravity. Now, so of course, n equals to 4 is related to supergravity in 5D or 10D, right? But that's type 2B. That's type 2B supergravity. If you really wanted to go to top down, then yes, I guess I'm making some statements about, but these are statements about the classical limit of the supergravity
yeah.
theory. But I think, okay, so at least at the 2 derivative level in 4 dimensions, yes, I think these statements should be true for the supergravity theory, provided that you're doing it in anti-de Sitter space. Okay, so anti-de Sitter is quite important here. But yeah, that should be true. Yeah, I think that should be true. For example, one open question that we don't know is whether the spectral duality relation that I was talking about here generalizes to higher derivative gravities. And of course, in supergravity, higher derivative corrections are important, and that's an open question. We don't know. This is all fairly new, so that remains to be seen. Okay, I hope this sort of answers a little bit your question.
Yeah, yes. It's just a curiosity, but thank you.
Yeah.
Okay, more questions. Well, I've got a question. I don't know if actually that makes sense, but I was wondering if you, in your slide 19, you mentioned a
19.
chaos point. 19? Yes, you mentioned a chaos point.
Yeah.
So I was wondering if this skipping phenomenon is related to the black hole event horizon.
It is. It's all of this is dictated by the event horizon. So what happens is, okay, so from the point of view of gravitational waves, so when you have a black hole, you always impose that your waves are infalling. So everything falls into the horizon. Yeah? And it just so happens that at these special pole skipping points, you cannot determine what is ingoing and what is outgoing. So at these special frequencies, you cannot impose boundary conditions at the horizon that would fix anything. So you always have a free solution that you can just add to it. And this is what then in the dual picture translates to this freedom. And this is why you get the 0 over 0. We explained this. So maybe this is most clearly explained in this JHEP paper. Mike Blake, Richard Davison, me, and Hong Liu from so this was Harvard MIT group, and there I think we most clearly explained how this works from the point of view of the horizon. And yeah, these are special points where the gravitational waves at the horizon are degenerate, and you cannot fix them by boundary condition. And this also relates to quantum chaos, because in holography, quantum chaos is also dictated by behavior at the horizon. It's the shock waves at the horizon, and then it turns out that actually pole skipping equation is equal to the shockwave equation always. So we already saw this, and then there was recently a proof in this paper, Chua, Hartman, Wang, the Cornell University group, Tom Hartman, and they actually proved that in general, there's always this connection between shockwaves at the horizon and our phenomenon of pole skipping. So this is now very well understood, yeah. But yeah, it's horizon, and all of this is horizon physics essentially, which is why it's all local. That's what I was talking about. Yeah, yeah. All of this is coming. So all of this is like reconstruction of the whole space-time by just looking at horizon properties. It's something like this. Yeah.
Okay. Thank you.
Thanks.
So more questions.
I have a question. You mentioned, can you hear me?
Yes, I can. Yeah.
You mentioned that you can use complex variable methods to study theory in different energy scales. Do you know if it is being used to study quantum gravity in different energy scales? Because quantum gravity is valid in the infrared limit. So could it be used to study quantum gravity in the electroweak energy scale?
No, I don't. I mean, certainly nobody has done anything like this. I don't know. I think that's a bit ambitious. Quantum gravity. Well, who knows? I mean, I it's unclear. So, for example, this how much you can reconstruct going from infrared to ultraviolet in a realistic QFT is not clear to me. But I mean, yes. So think of it as follows. So this is something like, let's say you knew the full chiral perturbation theory in QCD. You know, it's a gradient expansion, and you just have the coefficients of the gradient expansion of some field U. So from this, what I'm saying here is equivalent to being able to compute the masses of all of the mesons, something like this, okay? Now, can this help you to say something about a different field? I don't know. Can you say something about going from low energy gravity to higher energy gravity? Maybe. Maybe this is more like, I like to think about this Euler-Heisenberg Lagrangian in QED. Yeah, it's the kind of I'm thinking about this stuff. It's a good question. I cannot tell you anything precise. I can tell you that nobody has done it. But these are fairly new, to some extent, new methods. Although of course, you know, these analytic continuations of going from one state to another have been used before in quantum mechanics, for example, from going from ground state energy to first energy level. This is highly related. People there, you know, it's this phenomenon of level crossing. So these are also, you know, these complex analysis methods. So this is similar. I've never seen it being used to predict ultraviolet physics from IR. So yeah, I don't know.
Okay, thanks.
Okay, so more questions. Well, I think there are no more questions. So thank you for your presentation and for being here. So again, you're very welcome when you want to come to Mexico.
That would be great. Thank you all very much. Have a nice, I guess, rest of the day, and I guess Christmas holidays and everything is coming now. Yeah.
Yes.
Okay. Bye bye.
Okay.
Thank you.
Thank you. Bye.